Math 13 students, welcome. Here I have a short lecture for you on the material from Chapter 2, 2.1, Part 1 in particular. I'm going to share my screen and we'll get going. All right. So let me go ahead and get the slideshow started. There we are. All right, so Chapter 2. Section 2.1, frequency distributions. Part 1, we got some basic definitions for you here. Bit of an outline. We're going to go ahead and develop some basic terms for a frequency distribution. We will develop further useful metrics, and we will explore appropriate examples. A word about that word metrics, by the way. A metric is just a way to measure data. A common example is an average or a mean. There are others out there, and we'll spend a lot of time talking about them. First off, data is just a bunch of numbers, and it really needs some organization. The first step really is to organize our data. And when working with a large data set of visualizations, it helps us to understand the nature of the distribution of a data set. Some basic definitions. A frequency distribution shows how data are split among categories or classes by listing the categories along with the number or frequency of data values in each of them. A frequency distribution is usually for numeric values or data, but you'll also see categorical data used in addition to the numeric type of data. So let's talk a little bit about frequency distributions. Frequency distributions are often presented in table form. We've got a table here. It's on wait times for orders at a McDonald's restaurant in terms of seconds. The left-hand column is titled time, and it contains classes of times and seconds. The right-hand column contains frequency or counts. The classes you'll see appear in red. Those are those values there on the left. The first class, for example, is 75 to 124 seconds. We usually do not include units in tables such as these. Here's an example. We're going to work through our vocabulary using that McDonald's data. So there is our data. We're going to talk about the lower class limit here. The lower class limit is the smallest possible value that can belong to a class. You see them there in red: 75, 125, 175, 225, and 275. Notice those are the values that begin each class or category. The lower class limits you see listed there. Upper class limit. The upper class limit is the largest possible value that can belong to a class. Going back to our data, the largest possible value is found here in red. 124 seconds for the first class, 174, 224, 274, and 324 for the balance of classes there. Those are the upper class limits, the largest value you would be able to possibly find in any class. Note that these are limits. There is no guarantee that any of the data points actually are either, say, 75 or 124. Upper class limits, there we go. A more complicated and subtle notion is the notion of a class boundary. The class boundaries are numbers used to separate the classes, but without the gaps created by class limits. The class boundaries, 74.5, 124.5, 174.5, 224.5, 274.5, and 324.5. I put those up there first because this is the one that honestly is a bit subtle. The class boundaries actually fall between the end of one class and the beginning of the next. When I take a look at my data, I can see, for example, the second class limit falls between 124 and 125. Two confusing class limits, boundaries, excuse me, are the boundaries that initiate the first class and the boundary that closes the last class. The class midpoint, this is a value exactly halfway between an upper and a lower class limit. We actually need a formula here. You can see that formula. The midpoint is equal to upper class limit plus lower class limit. That's our numerator, and we'll divide that result by 2. So if we take a look at our data there, 99.5 is what I get when I add the upper and lower class limit and divide by 2 for the first class, 149.5, and so on and so forth. You can see them listed there. Class width is the difference between two consecutive upper or perhaps lower class limits. This one can be a little confusing for students. You'll notice that the first class begins at 75 and ends at the second class begins at 125. So I'll use my lower class limits, 125 minus 75, to find the width for the first class. And this works for all the classes except the last class. For the last class, I use upper class limits, so 324 minus 274, and again I get 50. So each class has a width of 50 seconds. Let's not forget our units. What is the size of our sample? To find the size of our sample, we'll need to sum the total number of observations, or the frequency. I'll have to add the 11, the 10, the 3, and the 2. 11 plus 24 plus 10 plus 3 plus 2 is equal to 50. So our sample size is n equals 50. How long do most people wait? Well, the class that begins with 125 seconds and ends with 174 seconds has 24 observations in it. So most people wait somewhere in that range, between 125 and 174 seconds. What is the first class boundary for this table? Here again, I want to really explore this notion of an initial class boundary. It's the value that instantiates or begins the first class, but it can't be part of the first class. So 74.5 is the first class boundary. How about the last class boundary for this table? It's got to be the value that closes off the last class. So it's got to be just a little bit bigger than 324. So 324 and a half, or 324.5, is the last class boundary for this table. These two are a little bit fussy to get to, so be careful when you're asked questions about the first and the last class boundary. Here's another example. We're going to use the data on student age in years. And I'm going to ask a question. Do all classes have an upper class limit? And I'll ask for an explanation in 1 to 2 complete sentences. If I take a look at my data, I notice that the last class begins at age 42, but has no upper class limit. So no, the last class, age greater than or equal to 42, has no upper class limit. Do all classes have the same width? Explain in 1 to 2 complete sentences. No. The last class, which has no defined width, as there is no upper class limit. So again, that last class is a little odd. Some more definitions. A relative frequency distribution replaces class counts by a relative frequency or proportion. Sometimes they are presented in terms of a percentage. Relative frequency is RF, and we need another little formula. we take a class count, and we divide it by total n for the sample size to find our relative frequency for each class or category. The sum of the relative frequencies must be very close to 1, or 100%. Here's example 3. Calculate the relative frequency for data on the Mickey D's data. So I have to calculate the relative frequency, and I'll need n. So we already know that n equals 50 is the total number of observations. We want to divide each class count by n. The first class, for example, has 11 observations. Divided by 50 gives me a relative frequency of 0.22, 22% if I was going the percentage format. The second class, 24 divided by 50, represents 48% of the data points, or 0.48 is the relative frequency. And you can see those guys come up there, and we'll put the rest of them up there too. So there they are, the relative frequencies for that particular data set. More definitions. The cumulative frequency distribution contains the sum of the frequencies for each class and all previous classes. So you want to think of a running total. Calculate the cumulative frequency for the data on student age. There's the data on student age, and I begin with the first class count, and we add class counts as we go. So the first class count is 16. The second class count, 16 plus 39 is 55. And I do that for all my classes. As I work my way through the table, you'll notice that the last class, 94, cumulative frequency is actually the sample size of this particular data set. So, in summary, we have defined some basic terms for a frequency distribution, developed useful metrics, basically relative and cumulative frequency distributions, and explored appropriate examples. This should get you through the material in the first part of 2.1. We have another discussion that will also be shown pretty quickly here, and I'll take care of that ASAP. That's the end. Thank you. And I'm going to stop my sharing now and end the meeting. Goodbye.